Okay, should I start? Yeah. Okay. Okay, are there questions from last time? No. Very good. So what I'll talk about today is quantum chaos and black holes, and what I'm going to say is mostly based on the paper by Schenker and Stanford. There are several papers by them. There is also a particular model that Kitai considered, which considered some of these issues also, and where he could calculate more explicitly some of the things I'm going to talk about. So if we have, let's first say a few things about classical chaos, right? So we have the classical phase space, and if we have a system that starts at some position in phase space, then the evolution will take it to other places in phase space. And if it is a chaotic system, we expect that it will essentially explore all the phase space. And not only that, but also if we start with a nearby trajectory, that this trajectory will end up with a point which is very different from the original point. Okay. So when we have chaos, we expect to have high sensitivity to the initial conditions. And so in other words, if we have, for example, the position at some time t, which is a function of the initial position and the initial momentum, okay, so that's this function. And so this function, if we see how sensitive it is to the initial variations, right, we expect that this should start growing, right? So let's say the square of this, for example, will start growing. And this quantity is the same as the Poisson bracket of Q of t with p of 0, right? Okay. So natural measure of how this is growing would be to, for example, take the square of this and average it over the phase space, for example. That would tell us the average growth, the average divergence of these trajectories. Now this growth, the things inside so around the specific point, you can start from a point and see how things start diverging. And typically this will go exponentially, like e to the lambda time. And this lambda is sometimes called the Lyapunov exponent, right? So that depends on which point you are expanding around in phase space, but you can view this as a kind of average Lyapunov exponent. So that's classical. Now imagine we have now a quantum system. And the simplest situation we could consider is system of spins. Well, first we could consider one spin, right? So a system of just one spin. So the wave function will evolve in a unitary fashion. And if you have two initial wave functions which are have some inner product between them, the unitary evolution would preserve this inner product. So there is no growth of chaos or anything. And if you think in terms of the state vector, that would be true in any system, that you have the state vector and it evolves unitarily, then the somehow distance or the inner product between two state vectors will remain constant in time. Now, a better measure of chaos is to think about what the operators are doing. So suppose that you have a system of spins. So you have spins at S1 up to Sn. Okay, these spins could be arranged along a line, or they could be all together, or whatever. So we have just all we are talking about is that we have a system of elementary operators, so let's say sigma matrices, and with the Hilbert space is a direct product of all the Hilbert spaces associated to each of the spins. And in this Hilbert space we have some Hamiltonian H, and we can consider the state. We can think about the problem in the Heisenberg picture. So we take the state as fixed, and now we look at the how the spins evolve in time. So, for example, we could take the spin in position number 1 and compute what it is at time t. So this is just simply the action of the evolution operator on the spin at 0, which is just the sigma matrix, and so on, where u, as usual, is e to the minus I t h t. Okay. Okay. So now there are different things that can happen to this spin. So it could be that when you take, let's say maybe the spins are all arranged on a line, and when you evolve, they just move cyclically, and so that's a simple thing that could happen. So if you did that, then the commutator between this spin and any other spin, well, would be non-zero only when the first spin hit the first one, but it would be zero otherwise. Right. Now, we can consider the analog of what we did here. So the analog of this quantity would be to say we just take the spin at time t, the spin 1 at time t, and let's say we take any other spin, let's say spin j at time 0, and then we consider this commutator, put in here a minus sign so that wants to be positive, and compute the expectation value in the initial state. So we have some initial state, and then we compute this expectation value. Or we could have a thermal state, and then we compute the thermal expectation value. So, but we compute this expectation value. And if these two spins start out being different, so at t equal to 0, this is 0, and then it might grow. And the intuition based on, for example, on this classical example, is that this commutator will start growing and will become of order 1. And this is what we find in many chaotic systems, and will be what we will call a chaotic system, will be situations where this commutator becomes of order 1. So this type of behavior is sometimes called scrambling behavior. So it's that the Hamiltonian is such that somehow takes this the initial spin and kind of distributes it all over the other spins. So let me be a little more clear. So in order for this commutator to be of order 1 with all the other spins, it means that if you were to actually expand the operator S1 of t at this time, it will involve sums of products of many of the other spins, so S1, S2, S3, etc. Right? Sums of products of this kind, so that the spins j, so any other spin will appear in many of these terms, right? And so we'll have, since different components could appear, we'll have non-trivial commutator. Now we are going to be interested in Hamiltonians that are somewhat local in the following sense. Not local in space, but by local what we mean here is that the Hamiltonian will be a sum of a finite number of terms that act on a few spins at a time. So let's say we could have terms like this: I, j, k, s1, s2, si, sj, sk. But let's say a finite number, so it involves only a finite number of spins. The spins don't need to be next to each other, so it could act on. So there is no structure of locality here in this Hamiltonian. We could have a theory which is local, and in a theory that is local, definitely we have this structure. But we could consider also a theory where we don't have this structure. And an example of a theory roughly like this is when we take, for example, engaged theories, and we have the matrix quantum mechanics. So we have terms that involve commutators of the matrices. And if we think of this commutator as harmonic oscillators, right, and we have the indices of the harmonic oscillator, so this term acts on 4 harmonic oscillators at the time, right, but not more than 4. Or if we had fermions, then we literally would have something like these spins, and it will act on the spins 4 at a time. But there is no, Very good. So in this type of systems, if we want, so in order to have a commutator which is non-zero with all of them, we need here to have a very long list of spins. And then basically in each time step you would expect that, let's say, the spin number 1, since the Hamiltonian has a finite number of terms, so let's say from the commutator of the Hamiltonian with the first spin, we might get at least 2 spins, right? So from the first spin in the first step, let's say, we'll get 2 spins, and then we act with the Hamiltonian again. On each of these 2 spins could at most give rise to 4 spins, right? And when we act again, and so on. And so in order to get to the whole chain, it would take of the order of log of the number of spin steps, right? And that would be the fastest we can So the complication in this operator is going to, it cannot grow immediately. It cannot be that at the first time step it gets infinitely complicated. So it has to be that as time is progressing, it's getting more and more complicated. And so we'll call the scrambling time the time at which the commutator becomes of order 1. So this is when the first time at which the commutator becomes of order 1. And this argument that we were just saying is that this number has to be somehow bigger than the log of n, with some prefactor that has to do with some properties of the system. And so it turns out that one can argue, we'll go a little bit through the argument later and the reasons for thinking about this. So this argument is some characteristic scale of the system, which in thermal systems would be the characteristics temperature. And one can compute the precise coefficient in front of this. And one can even write a general formula where you have 2 pi times the logarithm of the entropy of the system. So we expect under rather general conditions that we should have this behavior. I'll make a slightly more clear statement later. So, what remains, I'll try to explain. Right. So the scrambling time has to be bigger than this, and that we'll also see that black holes are the systems that scramble fastest, so that the scrambling time is actually equal to this. I'll try to explain the reasons for thinking that in a moment. So. So we are imagining that we are evolving with the Hamiltonian. So first term, let's say we expand in H, right? So we have S, and then we have H commutator S, right? So if so each H has 3 terms. Oh yeah, there would be 3. Yeah, sorry. Yeah, you could have 3, but the argument is the same. So there is some duplication, and then you the number is exponential. Yeah, it is. It doesn't hold. So if you take a completely very general random matrix, then we don't expect it to hold. And yeah, it doesn't hold. So you can write down a generic matrix, and it won't be true. Okay, so now we'll discuss a more general discussion, where we'll do the same thing, but we'll discuss it a little more generally. So we just change the notation. So we'll call W of t will be one of the operators, and B of 0 will be the other. So this is one of the operators, and this is some other. So in this context, I was calling it S0, and Sj, and S1. So these two, we're going to assume that they are Hermitian operators. And so we'll consider this commutator as a function of t. So we consider a general system. So this could even be a field theory. But if it is a field theory, we'll smear the local operators over some time, let's say of order beta, so as to have an operator who's such that when it acts on a state, it produces a normalizable state, right? So we want that psi, if we have the initial state, when we act with V, for example, we get a normalizable state. And we can further normalize it so that the eigenvalues are of order 1, so that V squared is of order 1. This we don't quite need, but just for you to think about it this way. So, but maybe since we don't quite need it, let's even erase it. So you should think of V as somewhat analogous to the spin operators. So operators which have bounded eigenvalues and are relatively simple in the field theory. Okay. So now we'll take this commutator, and we'll just expand this commutator and look at the various terms that we get. So we will get the expectation value of a few terms. And let's first write down the terms that you get from when the two are in the same orders. For example, V. So for example, we'll get minus V W v wv, for example, that's one term. And then from the other ordering, we'll get vw, right? And then from the opposite orderings, when one is in one order and the other is in the other order, we'll get v square w plus v w square v, okay? So we get this term, so all we've done is to expand the commutator. And this commutator, so there are some pieces here, some terms here which have whose size we can estimate, and some other terms which we are going to study in more detail. So let's first look at this term. So yeah, I forgot to say, I don't remember if I said, but B and W are Hermitian operators, right? This implies that this expectation value, so the expectation value of W v square v, can be viewed as the square of, as the norm of a state. Let's call this a state. Let's see, this one, we are going to call it chi2. Right? So this first term is the norm of a state, and the state is, so chi2 is just simply vw, right? Acting on the initial state psi. So when we take the adjoint, we get these operators in the other order, and we get this term, right? Similarly, the other one is a similar inner product with another state. So now we have the state chi1, which is w v psi, okay? So it's simply the operators acting in the other order. Of course, the difference between these two states is related to the commutator. So if the commutator is 0, these two states are equal, right? And then here we have terms that can be interpreted as the inner product between these two states. So for example, let's say this one involves chi2, chi1, and this one should be the other one, chi2, chi1. Okay. Okay, now, so what is going on here? So when t is equal to 0, we could assume that these two operators commute. So for example, they could correspond to, in a field theory, could be operators at different locations, or as in the spin case, spins in different locations. And that would imply that these two states are equal to each other, so the inner product is 0, and we'll have a cancellation between these terms and these terms, right? And then as time progresses, we are complicating more and more the structure of W, and these states will be generically orthogonal to each other. And if they're orthogonal to each other, then this term will go to 0, right? So this second term will go to 0, and the commutator will grow. So the commutator started at 0, and then will grow eventually to the sum of these two things, right? And notice these guys mean the norms of states are time independent. So these pieces here are time independent. Well, we expect, yeah, certainly we expect them to be time independent. Okay. So there is no reason, at least, to consider them decreasing. Now, so one thing we can do is focus on this type of correlator and try to understand why they decrease. Okay. So we expect them generically to decrease. So the way this commutator should behave is the following. Okay. So now we're going to define a function f of t given by chi2, chi1, and is the expectation values v w of t. So v is at 0, so v is always at 0. V of 0 and w of t. Now this is a correlator which is not in a very natural time ordering, right? So because if, let's say, t is positive, then this would be in the somehow wrong time order. But if t is negative, then this other one, the bra, would be in the wrong time ordering, to be viewed as something relatively simple that could arise in some simple calculation. So it's something that is not very easy to measure, but it's something we can think about. So now what we expect is that this function, and we'll see more arguments for this, but let me first say the statement we'd like to make. So we take the modulus of this function, and it should be it should start at some value, and it's time independent in the beginning. And if we think of these two operators as are in some sense very far from each other, or we have they are corresponding to two different fields in, let's say, the gravity dual description, or somehow distant parts of the system. Well, we'll see an example in a second. Then we expect it to be constant up to some small corrections. And the idea is that at some time, these corrections will become large, and then this will decrease. So that's the expected behavior, and this time is what we were calling as the scrambling time. So if we had a chaotic system, no matter how distant, or we try to separate the influence of one operator from the other, we try to separate some of the degrees of freedom from the other, eventually the interactions will catch on, and we'll have this decrease. Okay, so this is, it's nice to see this in the gravity example. So let's consider the gravity example. So we'll now consider a field theory that has a gravity dual. Yes?
Yeah. So I was just wondering if this is something we've proved based on the
linearity
of that Hamiltonian, or if it's just an expectation.
No, it's an expectation at this point, right? So we'll later say what we've proven, right? So yeah, this is what we want to argue, and right now I'm going to explain why we get this behavior in theories that have a gravity dual. So that's what we're going to do right now. Mm-hmm. So far there were all expectations, right? Yeah, and now, yeah, so, well, we expect, first of all, the first feature is that this should be independent of time. This we expect if we have a system, let's say if we have two spins that are very far from each other, we expect that they should be independent of time until somehow the signal gets to the other spin, right? This decrease is just the fact that the system is becoming chaotic. And then that it goes to zero is we expect it from randomness of the Hamiltonian. So you can you can argue that if you have a random Hamiltonian, the mean value of this thing should be 0. Okay, so now we consider. But I think this will become a little more clear after we see this example. So far, treat all of this as expectations and don't trust anything. And right now, I'm going to discuss one specific example where you see these things working and how they work in this particular case. Okay. So we're going to have a theory that has a gravity dual. So there will be some boundary, and we're only going to be interested in the time direction. So it could have a gauge gravity duality in any number of dimensions. And we are going to consider a background with a black hole. Okay, so we're considering the theory at finite temperature, some temperature beta. And so we have a black hole here. So we have the black hole horizon, for example. And okay, so that's the system we have. And now V and W will be some perturbation. So for example, V will be some perturbation which is mirrored. So it's not a local operator at the point, but let's say it's mirrored over some time of order beta to make it normalizable and make it nice. Okay. And so this operator will create some excitation that will propagate inwards. And we are going to be interested first. Let's think of this as a state. So we can, if we initially had the state psi and then we act with the operator, we get a new state, which is B0 psi, which it will be a state that will contain a particle, right? So it's the state with a particle that is propagating inwards, right? So this is the trajectory of the particle. Let me denote it by a solid line. But now if we consider this as a state, of course, we can also evolve this state now backwards in time. And then it will contain the particle here, reflecting from the boundary and going backwards. Okay. So this full state as a state contains a particle that comes out of this horizon, reflects from the boundary, and then goes inwards. Okay. Now consider the state, another state, where we have w of t times psi. Okay. So this was time 0. Let's say this time here is t. And in the same way, we'll create an excitation. So this creates an excitation going this way. But if we consider the full state, we also should be considering also an excitation that is coming this way. Okay, so an excitation coming this way and then reflecting from the boundary and going up. Okay, so now so the goal is to evaluate the inner products that we have over there. So what we'll try to do is evaluate those. Well, actually, this inner product here, we're going to evaluate directly the function f of t, which is the interesting function that is responsible for the behavior of the correlator. And okay, so what do we have? So first, let's consider w of t, v of 0. Right? Okay. Now, so first we have the state v of 0, right? And that contains a particle going this way, coming from this particle that is going up, right? And what we are doing here is we are creating another particle, and then we can extrapolate also this one backwards, right? Now, what we get after they collide, we'll get some mess if we want to try to evaluate it backwards. But at this time, this is the state that we have, right? Then we can, of course, extrapolate it backwards, and we'll discuss that in a second. The other thing we could do is consider the state v of 0, w of t. Okay. In this case, when we act with the second operator, which was some operator here at some earlier times, we note that they operate this state. So here, of course, we have the state psi. So this state contains, as we drawn there, contains a particle that is going up, and will, if we hadn't acted with anything here, it would reach the boundary at this location, right? But that's not what we do. We really act with something here, and so now we have a particle that comes in this direction. Okay. So this state has this simple description at early times, and then they collide and they will do something here in the future. So I mean, we could calculate what the result of the collision is, and we'll get something here in the future. But what we see is that the inner product of this times this, so which is what we have over there, is equal to the scattering amplitude in the bulk. So this is equal to the scattering process in the bulk. Scattering amplitude in the bulk. Right? Because what we need to do is to consider this is the state that is on the left, so we can think of that as the final state, and this is the initial state, right? And we just have the scattering amplitude. So what we really need to compute is we have this as the initial state and the other one as the final state. We need to compute this particular scattering amplitude. Okay. Now, there is one more feature. I just not to mess up the picture here, I didn't draw the horizon. But if let me. Of course, this whole process is occurring in the vicinity of a black hole, and that has some consequences. So let's discuss those consequences. So let me first ignore the interaction and draw both particles. So we have these particles that were coming here, and we also had the this particle, and we had to do something with this collision. Okay, but as we increase time, this time difference, this is going closer and closer to the horizon, And the actual proper energy of this collision, well, first of all, this collision will happen very in the near horizon region, where we can approximate this by Rindler space. And in that region, the time translation symmetries act as boosts. Okay. So if we go in the near horizon region, if we want to go from this configuration to this one, what we are doing is acting with we're boosting one line relative to the other, because we're time translating one relative to the other. And therefore, the center of mass energy, we're going to denote S. Don't confuse this S with the entropy. Maybe S is the center of mass energy, so the E center of mass energy, center of mass all squared. That is going to scale like, so as we boost it, it gets rescaled, and in ordinary Rindler coordinates, it would be rescaled like e to the t, right? But those were being coordinates where the temperature is 2 pi, so if the temperature is not 2 pi, this factor is just 2 pi over beta, okay? So in the vicinity of a black hole, we expect that S is scales in this way, so it grows exponentially, right? Okay, so we have some scattering amplitude, and what we are trying to see is how it grows with time. The other point we could say is, well, this. So when the scattering amplitude grows with time, and it's in ordinary field theory, the amplitude that grows fastest with energy is the gravitational amplitude, gravitational scattering, because if we have a theory of gravity, because gravity, the strength of gravity is proportional to the energy. And so this scattering amplitude will end up, I'll discuss this in a little more detail later, but will end up involving a factor of S, and of course some factors of G Newton. So it's something that starts being very small, because G Newton is very small, but it grows with S, and since S is growing with time, this is an effect that is growing with time. And that effect growing with time is the correction to the scattering amplitude. So the scattering amplitude, if we ignore the interaction, is just 1, right? So we have 1 plus some correction. And right now I was discussing the correction. Okay.
So is that S curly S one?
Oh yes, I won't have to forget to change to curly S. But well, please ask me, and then we make sure we all understand it. Okay, so now I'm going to make a small detour discussing scattering of high energy particles in gravity. First, I'll give you one kind of argument, and then I'll give you another argument. So the scattering amplitude, computed by just exchanging a graviton diagram. So we have the two particles that zoom past each other, and then we exchange a graviton. This goes like G Newton times S squared over T, and this is a general result for any. So the 1 over T comes from the propagator. T is related to the momentum transfer, or let's say these two lines are at some spatial distance. And the fact that in general you would get S to the spin of the this again is curly S to the spin of the particle that we exchange. So that's a general result, and that's the fastest grow you can have. I mean, there are other diagrams, but this is the one that grows fastest with S. Okay. And the factor of spin comes from the fact that you are contracting the indices of this particle with the momenta, let's say P minus and P plus of these particles, and the maximum number of momenta you can contract between these two has to do with how many indices this particle contains. So it's clear that. Any questions? No?
What if the theory had higher spin particles?
Yeah, so if the theory had higher spin particles, let's say the simplest case is, let's say it has one higher spin particle of spin 3, let's say. Then you will have a higher power here. And we'll discuss what happens in that case. For the moment, we'll assume we have gravity. Okay. So in gravity, we'll have this. And from the amplitude, you can compute this forward scattering amplitude, and it turns out that in this forward kinematics, the whole forward S matrix, there are many S's, unfortunately. Maybe I shouldn't write this one. So you will have the whole effect will be proportional to some phase shift. And we are just going to calculate it only to first order, this phase shift. And the first order expression of this phase shift is simply you take essentially the amplitude. I'm not explaining this formula, but we'll derive the same result that we derive from this formula in a second. So we just do the Fourier transform with respect to the transverse dimensions. And that gives something of the form. We'll derive this formula in a second, but I just wanted to connect it to the amplitude. So we get S. So this is again the S. And here T is equal to minus Q squared. So we insert this in this formula, and we get G Newton over the impact parameter to the value D minus 4. So this is the result if you have, let's say, some particle here. Unfortunately, the blackboard doesn't have enough dimensions for this. So we have the particles moving in the x plus, x minus direction, right? Very fast moving particles, but they are separated in the direction perpendicular to the blackboard, right? And B is the separation in that distance, in the perpendicular direction. Okay, so all I wanted to derive is that we have a factor of S, and as you asked, if you had another spin particle, we would have spin minus 1 here, right? And so now we'll okay, so this I didn't derive this formula, so now we'll give a slightly more complete derivation. So we'll calculate that by first by thinking about this high energy scattering process in gravity. So we have the direction x minus and x plus, and we have a fast moving particle moving along this direction, and another fast moving particle. So let me draw the fast moving particle here. So that's one fast moving particle, and then we have another one. However, we can think of the interaction between the two as this fast moving particle creates a gravitational field, and then we'll just calculate the trajectory of the other particle in the first particle gravitational field. Now, it turns out that the gravitational field of a fast-moving particle is actually relatively simple. So it's so in this case that the particle is concentrated. Okay, so here I took so the fast-moving particle here is concentrated in the x minus direction. Unfortunately, in my notes I have it the other way, and if I try to switch it, I'll get it wrong. So let's say we have the fast-moving particle, which is localized along the x plus direction. This is not very localized, sorry. Along the x plus direction, then we have a correction to the metric that involves dx plus squared times some delta function of x plus, and then some function here of the transverse directions, function of y perpendicular, and here we have all the perpendicular directions, right? And this function ends up being equal to G Newton times the p plus of this fast-moving particle divided by y to the d minus 4. Okay, so the function that appears here should be a solution of the Laplace equation in the transverse dimensions, and this is the solution for a point like source. You can get this metric by taking, for example, the Schwarzschild metric and boosting. So you take the limit of the mass going to 0 and the boost parameter to infinity, keeping p plus fixed. And so for what happens is that the whole fields concentrate, all the gravitational field somehow concentrates on the x plus direction, and for any other position, you simply get 0. So when you take the mass to 0, so if you are very naive, you take this limit, you take the mass of Schwarzschild to 0, you get 0. I mean, you get the flat metric. And that's what you get almost everywhere except at this position. So this is one way to get this metric. Okay. And now we have another particle that will cross. So we have the particle that is.
Just some intuition about this term, about the metric the length because there's the mass there or something? Is that a symbolic notion?
Yeah, so the point is that when we do the boost, we are increasing some components of the metric. So the plus component of the metric gets rescaled, right? And so that's basically what's going on here. No, it's the same one that appears here. So the solution has a translation symmetry along x minus, right? So here we have the translation symmetry along x minus, and the particle has momentum p plus, so it has p minus almost 0, right? P lower minus almost 0, and p lower plus. Do I have it? Yeah, p lower plus non-zero, so it's localized along the plus direction, right? So the wave function is useful here not to get confused with pluses and minuses. I used to get very confused about which was plus and which was minus, but the good rule is to always put the index down. Then you remember that the indices are always contracted in this way, and the wave function of this particle will have a non-zero p plus, so it means that it can be very localized in x plus, right? And that's what we have here. Okay, so now we get we get the second probe particle, and we send the probe particle here at some coordinate. The probe particle has the opposite momentum. So this particle has p plus very large, much bigger than 1, and this one has p minus much bigger than 1, right? So we're going to ignore the other components of the momentum. So we have the other particle that comes in here and goes through this metric. And we'll treat the second particle as a probe. So this will be a geodesic in this metric. Okay, what will happen to the geodesic when it goes through a metric with this funny discontinuity, this funny delta function? In order to figure that out, it's convenient to do a coordinate transformation that removes the delta function. So let's imagine that so the second particle is going to be sitting at some transverse dimension. Again, the blackboard doesn't have enough dimensions. This particle is, let's say this one is on the blackboard, and this one will be away from the blackboard around here. It will be coming in and will feel the shock that the shock is extended all along this direction. And so we can do a change of coordinates to remove the delta function. And we'll do a change of coordinates that removes the delta function at the position y0, where the geodesic is sitting. So that geodesic is sitting at a fixed y0. And one way we can do that is by redefining the... so we define a new x minus, let's say x tilde minus coordinate, which will be the minus coordinate plus this f of y0 times some theta of of x plus. Okay. Okay. So now if we had a metric which is just d tilde minus dx plus with no other, well, what the dy also, and we insert this term in the metric, then what we see is that we generate from this we generate a delta function of x plus times some other dx plus, so we get dx plus squared. So we generate a term that looks like this. It certainly looks like this at y0, right? And so the metric in these coordinates will have the form with some f of the same f of y minus f of y0 times the delta function. So this one vanishes at the. So the point here is to make this one vanish at the point where the geodesic crosses the shock. And so so now we have, at least at this point, we have a continuous metric in the plus and minus directions. And so we expect the geodesic then to move continuously across this shock for this reason. And so however, that so in other words, the x value of x minus before the shock and after the shock we expect it to be the same, but the value of this x minus will be different because of this step function. And so what we get is that on the other side of the shock, we find that the particle emerges, so in the original coordinates, it emerges as a different value of x minus, okay, displaced from the original by some delta x minus, And this displacement is precisely this thing here. So we have that delta x minus is equal to this f of y0, and that was g Newton p minus p plus. So p plus, that's the momentum of the shock, divided by b to the d minus 4, okay, or y0 to the d minus 4. So y0 is the same thing that I was calling b over there, so it's the impact parameter, so we can call it b already here. Okay. Now this formula is very close relative to some interesting effect in general relativity, which is called the Shapiro time delay. So you might be familiar, well, maybe some of you might have, well, maybe I'll explain. So Einstein realized that if you take light from a distant source and it goes near the sun, it gets bent a little bit, right? And it took several years for Shapiro in the 60s to realize that it also, when you have light going near a massive object and you send a light pulse, this light pulse gets delayed a little bit. There is a small time delay. And this, so you can take the expression that, well, this expression is just a close relative, and it's a time delay. So this particle emerges from the shock a bit later than it would have emerged if it just gone through, but not earlier. Okay, so it comes out a bit later. It's important it's a delay, not an advance. For if it was an advance, it would violate asymptotic causality. Okay. And this description with the shock waves and so on was given by Toft and Drey, basically by thinking about this problem of scattering near a black hole. And so we can write if we have the incoming, let's say we have the incoming wave function of the minus particle, right? Then we can write the outgoing. This is just restating all these results. I'm not doing anything here. So the wave function after the shock is equal to the wave function before the shock plus this displacement. Okay. I mean, of course, when the particle goes through the shock, it also gets bent a little bit, but we are going to ignore this bending. So the main effect will be this displacement. The bending is not important because the bending angle gets smaller and smaller as you go to higher and higher energies. But sorry. Yeah. Okay, well, now we have this, and this we can write as e to the I b minus this delta x minus. And delta x minus is the expression we wrote over there. And this is, again, e to the I g Newton p plus p minus over b to the d minus 4, which is the formula that I probably erased here. No, didn't. So, which is this formula, okay? Where this becomes the Maldacena variable s, okay? So I'm just trying to connect these formulas, not doing anything here. Okay, so what all this says is that the inner product between psi 1 and psi 2, which is what we were computing. Did I erase it already? Yes. So we were interested in computing the inner product between psi 1 and psi 2. And that is equal to, well, essentially the modulus of e to the I delta. But we're always expanding everything to first order. So we have 1 plus I g Newton over. So g Newton times s, and s is going like e to the t times 2 pi over beta. Okay. So we took this expression for delta, and we find that we have to decide what exactly b is. And b becomes essentially some distance of the order of the radius of the black hole, or the radius of the particles. So if we have only one scale, like we have a black hole in ADS, we have just the radius of ADS. And this could also be viewed as 1 plus I well, this effect goes like 1 over n, so this is a small effect, e to the t 2 pi over beta. Now, in this particular case of gravity, this actually doesn't decrease because we have an I. At least to this order, it doesn't decrease because we have an I. So if we would take the square of this, then we'd need to calculate this to second order to see exactly what is happening, right? Because in principle, this modulus should actually decrease. So what we see is here is not quite decreasing. However, we expect from this picture of the displacement that it should decrease, right? So the picture of the scattering process, the final picture that we get, is the following. So we had those diagrams that we were writing here, and we were interested in computing the scattering amplitude between this. So this is the overlap of the two states. Where is the yellow chalk? We are interested in computing this overlap, right? So this is the initial state, this is the out state. But if we really follow the bottom state, what we have just said is that these guys both get some time delay, right? So this gets some time delay, and this other one also gets some time delay. So they are emerging a little displaced relative. So I basically discussed the time delay, the time displacement of only one. But if we have them equal, you can check that, well, that phase shift over there displaces actually both of them. But anyway, so the point is that they are displaced. So this is the actual state that we have, and we want to compute the overlap with this state that we have here and this state that we have over here, right? And so as the displacement gets bigger and bigger, we see that the overlap is going to get smaller and smaller. Okay, so that's the statement we were saying before, that this correlator will decay. So we see that it's decaying because of the growth of the gravitational interactions. So it's basically gravitational interactions are acting and they are disrupting the state. So we don't have, it would be 1 if we didn't have any interactions, but we have some interactions and it's going to other states, to other, let's say, orthogonal states. And the orthogonal state in this case is pretty simple to understand. It's just displacements of the original one. At least this is what happens when the gravity is relatively weak. Okay, so that's, there you see a little more of why this is decaying. And this is not yet quite decaying. And it's interesting that that this commutator that we expected to grow just from the chaotic nature of the Hamiltonian and so on, here is growing because of the increase with energy of gravity. And so also there is the universality of gravity that affects all particles. And also chaos will eventually affect everything. So that was also pretty interesting. So this discussion, the fact that these interactions are becoming large near the black hole horizon was noted by Dre and Toft, but it was never clear how to make good use of those effects. And this discussion of chaos makes good use of these effects by giving a nice interpretation for what it means. Okay. Now, if we have string theory as opposed to gravity, so now we suppose we have string theory. So we will need to understand the behavior of the amplitude at large S in string theory. And so for S and T. And you can take the Veneziano amplitude, well, more properly the Shapiro amplitude, the closed string amplitude, and find that, well, in gravity we had 2 here, and in string theory we get an alpha prime T, this is so-called the Ricci behavior. So this is the behavior of the amplitude when S is very large and T is finite. And in our kinematic configuration, T is space-like, so it's negative with our conventions. So this is really S to the 2 minus something, right? Now in the phase shift, what appears there is the phase shift, which is the amplitude divided by S. So this really, at the level of delta, this is S to the 1 minus something. And if you are a little bit more careful with factors of I and so on, what really appears in the Veneziano amplitude is this with an I. So here you end up with an extra I. And the fact that the exponent is now not 1 anymore implies that this coefficient here, when you go to the case of string theory, you will get 1 minus something which has a real part times e to the t times 2 pi over beta times some number which is 1 minus something small, let's say 1 minus epsilon. And this epsilon, so this is the behavior of this inner product. So we're writing an equality here. So we had 1, which is with no interactions, then something of order epsilon, but real. Of course, we have the 1 over n squared, which is related to 1 over g string to g string squared. And we get a reduction of the growth. So it grows more slowly. And epsilon in black holes in ADS or more or less flat-space black holes has, well, this I'm not telling you the derivation. So alpha prime is L string squared. It's an effect of order alpha prime, and the question is exactly what is t. And t is something of the order of the radius of curvature. So it's an effect which, if we are in the close to the gravity regime where this is small, it will be a small effect. Okay. So it gives a reduction to the growth of this commutator. Now you could imagine you take a weakly coupled theory, and if you have, let's say, perturbative Young mills, you can, well, I guess I haven't discussed this. Well, maybe I'll discuss it later. Okay. Now this phase shift is, I briefly said that it was constrained by causality, and it turns out that, okay, well, I might not explain this complete. So if you had, let me see what's the simplest way to explain this. Well, let me just state the answer. So this phase shift, if you think of this, so let's think just in terms of the p minus variable. So we went through some shock, and we think in terms of the p minus variable. So this is telling us how the out wave function is related to the in wave function in momentum space. So psi out. So we first put it in position space, but now we can say we have this factor times the psi in momentum space. So here we have only just one variable, and if we demand that we have time delays and not time advances, and that the norm of this function is less than the norm of this function, then we get by the usual arguments related to the connection between causality and analyticity, we find that this whole function is analytic in the upper half plane, and e to the I delta and its modulus is less than 1 in the upper half plane. Okay. I didn't explain completely where this comes from, but you might have seen it in the context of index of refractions and so on in optics. And if not, well, we could discuss it a bit more. Now, if we had a delta, so I was asked whether if we had a delta that corresponds to a particle of higher spin, then we will get here an A with an A bigger than 1, where A would be the spin of the particle. So A is equal to spin minus 1, right? So if we have a spin 3 or higher, this would be bigger than 1. And if you have such a function, so this P minus translates into essentially the complex S plane. So this is a function that will have growth or decay. So this, in order for this to decay, we need that the imaginary part of this it has a uniform sign everywhere in the upper half plane, right? It's, let's say, always negative. Okay. And in that case, but that is possible only if A is less than 1, because as we change the angle, so let's say this is S and this is the angle in the complex variable S, let me call it phi, then we'll get here some factors of sine of A phi, and this can have a uniform sign from 0 to 2 pi only if A is less than 1. right? Otherwise, there will be a change in sign, right? Okay. So if you had a single higher spin particle, you would violate causality. If you had, but in string theory, we don't have a single higher spin particle. We have a whole set of higher spin particles. And the whole set conspires in such a way that actually, after you sum them all, you actually doesn't increase, but it actually decreases, even decreases faster than gravity. Well, it increases less slowly than gravity. That's a better way to say it. Okay. So from these causality constraints, we expect that in a gravity theory that is subject to causality constraints, this function f should decrease with an exponent, with the Lyapunov exponent here. So this is the coefficient of the divergence here from 1, so how it starts decreasing. That should be less or equal than 2 pi over beta. So this is lambda, should be less or equal, the exponent is less or equal than 2 pi over beta. And it turns out that this type of behavior, here I have argued for it using the fact that we have a theory with a gravity dual and trying to use some arguments of causality in that theory. But one can argue for this bound under very general assumptions for rather general field theories. So not even field theories or even quantum mechanical systems. So if you have a quantum mechanical system which initially contains some isolated parts because, let's say, it has some special extent or a large number of degrees of freedom, but it has a Hamiltonian with the property I mentioned that it involves a few spins at a time. Then, when you let this system evolve, it will lead to a behavior in the correlator of this form. To be a little more precise, the one for which the correlator for which the theorem actually applies is for a very close relative to the one we are considering. Is for actually, so the function for which one can argue this property is a function of t, which is, for example, in this kind of thermal expectation value, but not quite, v y w of t. Okay, and y is just the fourth root of the thermal factor. Okay. So if we were doing, so in what I said so far up to now, we just were putting the factor of y only in one side of the correlator. So we're putting all these factors of y to one side. Okay. So we have the thermal correlator. That's in what I've said so far. But the one that has a slightly nicer behavior is this one. And this you can view as, so we have the thermal circle, right, which has length 2 pi. And so we are inserting, let's say, one v. Let's say we start with this v and we start moving to the left. And then after moving a quarter distance, we insert the w, but after moving in Lorentzian signature. And then we have the other b. And then we come to the second w, which we also displace in Lorentzian signature. And then we come back to the original one. So that's one way we can think about this computation. So the w's are inserted here, and the v's are inserted here. And well, so this has nicer properties, it's real, and so on. And this is the one that for which one can prove that it behaves like 1 minus some quantity of order 1 over n squared, or 1 over the entropy. So maybe I should call it 1 over the entropy with some number times e to the lambda of t. And this lambda should obey this inequality. Okay. Now this is somewhat related to what we were discussing. So in order to get to something that is a little more related to the amplitudes, what one needs is to take this function, and we can analytically continue in this time. So that would rotate these two insertions, and we can go to analytic continuation of time where we put the two insertions, put these two w's actually at so we get v and then a w here, and then v and a w here. And this is a calculation that can be interpreted in terms of the thermofield double. So this is a computation in the thermofield double. I'll move to the other blackboard. Where you have one operator on one side. So these are the two sides. This is just in the field theory. This I don't need. Well, we don't necessarily have a gravity dual, but corresponds in the thermofield double picture to a correlator where you have a W here, a W here, a V here, and a V here. And it turns out that the time ordering. So now assume you have a gravity dual. So let's say we have a gravity dual. So we have something like the thermofield double. And the continuation here, the ordering of the operators is such that this correlator precisely corresponds to scattering amplitude in this thermofield double. So it precisely corresponds to this particular correlator with the natural ordering you have in the thermofield double. Okay. And so if you have a gravity dual, you might think in terms of particles that some scattering amplitude between these particles. Of course, a particle here cannot make it out here, so it's always going to be somewhat space-like. So this thermofield double connection is also interesting to consider in the case that, forget about now theories that have gravity dual, let's consider a field theory in flat space, right? Just Minkowski space. But let's view Minkowski space as a system at finite temperature. So it's now a system at finite temperature of the right Rindler wedge and the left Rindler wedge. Okay. And in this case, we can also think of this as a particular example of this general discussion, and think of, let's say, V as two operators inserted at this location, so V and V, and then W, we could have operators that are inserted here, but then we do the time displacements appropriate to boosts around the origin. So we boost this operator, so we take this other operator to be at this location, W of t. Okay. And as I said, the ordering of the operators inside that trace is exactly the one you would expect if you were to compute this correlator in the standard ordering, the ordering given by the actual Minkowski times in this picture. So in this context, the constraint, that constraint regarding that constraint on lambda is a constraint on how fast that correlator can grow when we increase the time, and this is related to something called the Regge behavior in the field theory. And so normally in Regge theory, we say that the amplitudes can increase as s to some power which we call j, and j does not need to be an integer. But what this argument shows is that whatever this is, this j should be less or equal than 2. Okay, it's like this effective spin should be less than the spin of the graviton. And this is an argument that is correct for the leading order correction in the 1/n expansion, and analyzing the largest behavior of that leading order correction. Okay, any questions? Yep. Yeah, so let me, perhaps I should say this more slowly. And remember when we were talking about thermofield doubles, how do we generate the thermofield double state, right? So we do an evolution in, maybe I shouldn't have erased this. So to generate the thermofield double state, we do an evolution in Euclidean time over half of a Euclidean circle, right? A circle which is of length half of beta, right? So in Euclidean time, we evolve over beta over 2, and then this is all Euclidean, and then we go to Lorentzian signature, and we have the system in Lorentzian signature, right? Right. So if we were inserting operators here, so we could insert some operators v here at equal to 0, and then some at non-zero times, right? So we could insert here the operators at some other times, and then take the the thermal field double state in the future and compute those correlators, right? So those are the correlators computed in the thermal field double state are correlators where we put the thermal field double state here in the past and the thermal field double state here in the future, right? So if we have something which is not at t equal to 0, it's convenient to evolve it to some time and then go back to t equal to 0 where we had this simple picture, right? So here we're just evolving this in time and we are evolving the other one also in time, right? So this is how we can get the W of t and right, by doing these time evolutions. And you can see that the orderings between v and so here with the picture I've drawn does not correspond to that correlator because we have v, so the two v's are next to each other, and then we have the w. So a picture that corresponds to that correlator is more like the v here, right? But this is precisely the time ordering that we would use to do this computation with the proper time ordering, right? Is that clear? Maybe I should pause. Should I explain this business of time ordering a little more? Well, let's. I won't explain. Okay, fine. So summary. So the summary is that one can argue for this bound with fairly minimal physical assumptions, and this bound then is a bound on chaos, on the development of chaos, and it has some implications. Now we can go back, and this bound also has some implications for scattering amplitudes if the theory has a gravity dual. If the theory doesn't have a gravity dual, it also has some implications even for this Regge behavior in just simply flat space. And more generally, in the context of the theories that have a gravity dual and have a black hole background, is an interesting application of the fact that the scattering amplitudes grow near the black hole horizon, and it's telling us what this means. So.
The theory with the ADS dual, this bound applies at strong coupling or at any coupling?
This bound applies at any coupling. Yeah, maybe I should. Yeah, so this bound. No, because this is a field theory argument. So okay, maybe I wasn't clear enough. In this picture, I was jumping too much between different cases. So that chaos bound is valid for any quantum system, even a quantum billiard or whatever. So you have that bound, and in particular, we can apply to the Rindler wedge. Okay, so we take a Rindler wedge, and then if you take the form that is in the picture in the rightmost picture there in the blackboard, it corresponds to doing a half evolution in Euclidean time of the Rindler wedge, and that produces the other Rindler wedge. The thermal field double of the Rindler wedge is just all Minkowski space, and then it translates into a statement in Minkowski space. So this is a statement in Minkowski space. It doesn't have to be a CFT, for example. It's a statement in field theory in Minkowski space. We don't need a gravity dual. So, yeah. No. But maybe if I said it incorrect. So here, no gravity dual. Okay. Yeah. Okay. Right. So why did we talk about? So the gravity dual was useful for motivating and giving an example of this bound and just showing why it is particularly interesting. It's particularly somehow saying that this geometry near the horizon of the black hole is encoding the chaotic nature of the dynamics of the system, and that should figure in the theory, right? So the reason probably means that the reason we appear to lose information has to do with the fact that we have this chaotic dynamics and we are doing some kind of average, and for that reason we appear to lose information. Of course, this doesn't solve the problems, the modern version of the information paradox, which is to explain how the preservation of information from the outside is really consistent with a smooth interior. Okay, so it's not giving a construction of the interior. Everything that we discussed here was outside the black hole horizon. Okay. And any other question? Yeah. 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 So that's right. So the time. So there, what happened was that when you displace in time, right? You put these operators at very displaced times. It's happening in the near horizon region, and there time displacements corresponds to boosts. I mean, that's what happens if you have a black hole. For this bound there, we don't need a black hole anywhere. Yes, exactly. So the decay in the overlap is related. So in the gravity picture, it's related just to the scattering and this time shifts. It's the fact that when you do high energy scattering, the wave packets get shifted, and then they don't have an overlap with the unshifted ones. Is that clear? I mean, that should be. If I didn't explain this clearly, that I failed. Yeah. Yes.
I have a question about this. So you say that there's some amplitude or some power there that depends on the particle spin. But then you said over there that
Yeah. This I perhaps rushed, but this J is not an integer. It's not the spin of any particle. This J is some number. Sometimes people call it the spin of the region, but I don't understand well enough what the region is. But let me just say some number, which, for example, could depend on lambda, right? And for example, in n equal to 4 super Young mills, this J, when lambda, so as a function of lambda, so now we have this J as a function of lambda. So it starts out at 1, and in the gravity limit we saw it was 2, right? And so it's going to have it has a behavior of this form. And maybe Pedro will tell you how to compute it using integrability. So you have this behavior, but let's, for example, comment a little more on what happens near 1. So we saw that the rate of increase of those correlates. So in that case, the behavior of those correlators would be proportional to, we said it was s to the spin minus 1, and this will grow in like e to the t times 2 pi over beta. And in this case, the coefficient, so because we subtracted the 1, the coefficient will be of order lambda to lead in order in the coupling. This lambda is not the Lyapunov exponent, but the Toft coupling of the gauge theory, right? And so it's very small, so it's increasing very slowly. So this is saying is that in free field theories, the development of, or almost free field theories, weakly coupled field theories, the development of chaos is slow. I mean, if you have if you have two separate systems, it takes a while for systems to interact and somehow thermalize and influence each other. Okay. So at weak coupling is slow, and at strong coupling is as strong as it could possibly be. So, yeah.
I'm sorry, is this saying then that we can't have some particle higher spin?
Exactly, yes. If you have a single particle of higher spin, it will violate the bound and it will not work. In string theory, we have higher spin particles, but we have a whole series of particles, and because of that, the final behavior is not that of a single higher spin particles. In some sense, there are cancellations between different spins. Well, that's one way of